Hello, today I am presenting my advanced signal processing project titled Real-Time State of Charge Estimation for Lithium-Ion Batteries using an extended Kalman filtering framework. The primary motivation behind this work is to establish a foundational benchmark for clean battery management topologies, focusing heavily on safety and efficiency. As we know, the core electromechanical environment of a lithium-ion battery cannot be quantified directly via standard physical telemetry. Therefore, mathematical observer notes an imperative. Traditional open loop approaches such as column counting suffer from unbound integration drift over extending operational regimes due to current sensor biases. On the other hand, static voltage lookup tables entirely fail under intensive dynamic loads because they neglect transient battery profiles. To overcome these structural limitations, this project implements a robust module-based observer. So first, let's look at the mathematical foundation. As illustrated in this picture, this equivalent circuit replicates the electronic behavior of the battery cell. The internal battery structure features an open circuit voltage source, an internal ohmic resistance, and a parallel R1 and C1 polarization network that dictates the slow relaxation dynamics and transient voltage diffusion barriers. These internal dynamics are mapped directly alongside the load current to the external terminal connections. Mathematically, our system vector xk comprises two primary internal states, the state of charge itself and the RC diffusion voltage barrier. Driven by the input current vector, the linear stochastic state transition behavior is governed by the discrete state space equation shown on the slides, where the T dictates the relaxation dynamics and Q beta specifies the physical battery capacity, and Vk tracks the process noise covariance vector modeled to mitigate thermal fluctuations. Moving on the measurement model, our observation equation routes the internal states to the terminal output voltage, Zk. It combines a highly nonlinear open circuit voltage profile, OCV, with the structural resistance drops across the internal resistance. As you can see in here, that to embed this highly nonlinear profile seamlessly into the extended Kalman pipeline, analytical linearization yields our dynamic measurement matrix via the precise evaluation of the Jacobian operator. A key implementation milestone in our architecture was completely eliminating any dependency on the MATLAB symbolic math toolbox by deriving the exact analytical derivatives and hard-coding the Jacobian matrix directly into our custom processing core, Analyze Engine V2. We achieved a highly streamlined standalone execution train. So in real-world deployment, standard static EKF topologies decrease significantly during long-term operational schedules as a direct consequence of cell degradation. Battery aging causes a severe upward drift in internal resistance, creating an expanding model mismatch that forces the baseline EKF to eventually diverge. To address this degradation loop, we scaled our system into a joint EKF architecture. The state vector is augmented online to track the parameter drift simultaneously. This allows filter to co-estimate both the dynamic states and the time-varying internal resistance parameters simultaneously online. Furthermore, during our covariance tuning phase, the process noise covariance matrix Q was intentionally turned up from 10 power minus 7 to 10 power minus 5. This strategic adjustments penalized state model dependencies, elevates the Kalman gain parameters, and forces the filter to prioritize dynamic feedback measurements from low voltage sensor innovations. For experimental validation, the framework was strongly verified using the benchmark NASA battery datasets. As shown in the figure, we analyzed nominal operational schedules using discharge cycle 2 of the B0005 cell. The top subplots highlights an expectationally precise voltage tracking response with a minimum mean absolute error of just 0.0851 voltage. The middle subplot tracks the stable online convergence of the state of charge. Critically, the bottom subplot demonstrates the power of the joint EKF. It successfully captures the true parameter adaptation of the internal resistance as it dynamically shifts from 0.1 ohm to 0.1598 ohm over the 70 minutes window, effectively eliminating model mismatch. To evaluate long-term multi-cycle performance and statistical error limits, let's look at this figure. While cycle 2 represents a nominal regime with tight tracking, testing under cycle 150, representing a severely aged regime, reveals that the standard EKF tracks with a persistent static error offset due to unmodeled ohmic shifts. The proposed joint EKF completely compromises those tracking residuals back to a zero mean band across various cells and diverse aging regimes. Our adaptive variant tuning successfully bounds the goal tracking error tightly near the calculated mean MAA threshold. In summary, the entire dynamic system runs smoothly on the modular analysis engineer V2. It processes large data batches efficiently without requiring any external tools or symbolic packages, making it perfectly optimized for immediate deployment in autonomous safety and electric vehicle applications. Our online co-estimation algorithm guarantees real-time resilient operation even as the underlying hardware undergoes intensive degradation. Thank you for your time. Have a good day.